So my name is Guillaume Prats. Today, in this video, I'm going to talk about the representation of images. So using both the spatial domain, which is the normal way we represent images, but I also want to introduce this idea of representing images in the frequency domain. And especially, we will see later in the class why we want to represent images in the frequency domain and how it's useful in terms of tomographic imaging. Okay, so I'll just get started right away with a simple question: what is an image? So, earlier in the class, you've learned about medical imaging, especially radionuclide imaging. And so we're going to assume we have a patient that's coming to the hospital for a scan, and they have potentially something wrong, and we're trying to see what's going on. So they're going to be receiving an injection of a radiotracer, which can distribute in the whole body. And we want to look at the distribution of the radiotracer in 3 dimensions. And so specifically here, I'm going to look at the distribution of the radiotracer across the abdomen in the plane shown as a dashed line. And this is going to be represented as mathematically represented as a function of 2 variables. So if I try to draw the distribution of the tracer across this cross section, it's going to look like this is the abdomen of the patient, and maybe there's a region of the abdomen where the tracer has accumulated more intensely because of an underlying medical condition, for example. So mathematically, this here is a function because it's a physical quantity. It's the distribution of the radiotracer. It's concentration over space. And it's a function of 2 variables, f of x and y, where x and y are the coordinates in the plane, shown like here. So of course, we can look at multiple planes, and if we look at multiple planes, then this becomes, so this would be in 2D. In 3D, it becomes a function of 3 variables. It's an additional z variable, which is the dimension perpendicular to the plane. So because this is a continuous function, and we're using computer to acquire these images and represent them onto the computer monitor, we have to discretize the images into pixels. Okay, so pixels is the smallest element in an image, and actually pixel means picture element. And so an image is essentially represented as an array of those pixels. So it's a 2-dimensional. So we have a 2-dimensional image. It's a 2-dimensional array of pixels, and each pixel is a number. Okay, so the pixels can take, for example, integer values. So if we're looking at the number of radioactive count detected per pixel, so these would be numbers such as 1, 2, 3, and so on. Or it could be a real valued number. So decimal numbers. In the end, we have to represent the image onto a computer screen, which has limited number of gray level that it can represent. Typically, a computer monitor can represent only about 256 different shades of gray. So 256 gray levels. So, but anyway, so this is what we have in 2 dimensions. So we have the image that's represented as an array of number. And so, essentially the numbers are going to be higher wherever we have maybe a higher radioactivity, and then they're going to be lower in different region, and that allows us to create a distribution, at least a representation of the distribution that's computable by the computer. And so in 3D, how do we represent a 3-dimensional distribution of radiotracer? It's going to be very simple. It's going to be a stack of these 2D images. So if we consider a stack of 2D images, such as this one, then we have a 3-dimensional distribution of the tracer now. Okay, so then the coordinates here, we have y that's here, x that's here, and then z, which is shown here. So now I would like to talk about the frequency domain and how to represent images in the frequency domain. And so I'm going to step back a little bit and talk about a simple type of signal, which is a 1-dimensional signal. So images are functions of space. Here we're going to consider a a sound signal, which is a function of time. So a sound signal can be represented as the amplitude of the sound over time. So this is, for example, a typical sound signal where the y-axis is amplitude and then the x-axis is time. And so what's very important to understand here is that if we have any signal, any real signal, can actually be decomposed in terms of pure frequencies. And so what I mean by this is that there's those so-called pure frequency signals that can be combined in different ways to give any existing signal that's measurable. So a pure frequency signal would be something like a sine wave. And so again, if we consider a signal as a function of time, or a cosine wave, let's look at a cosine wave. So a cosine wave would have pretty characteristic shape like this. And it's characterized by 3 parameters. So first, it's characterized by its amplitude. So that's the amplitude of the sine wave. It can be characterized by its frequency, so that's how many times it will cycle up and down per second. So that's going to be the frequency. And then it's also characterized by its phase. And then here the phase is actually 0. In this example, that's the phase. So those 3 parameters. And so when we do frequency analysis of a signal, we can actually represent any signal as an infinite sum of an infinite number of sine waves. And so to represent this in a non-mathematical term, a non-mathematical way, is that this signal I've drawn on the left can be written as a very large sum of sine waves with different frequencies and different phases and different amplitude. So this is going to be plus, for example, we could have this sine wave here that maybe has a slightly higher frequency, so there's more cycles per second, and then plus this sine wave, let me show here, which maybe has very, very high frequency here. And so all these sine waves have different amplitude. So this is the amplitude, and then they may have different phase also. So this is the phase. And then the frequency is this related to the number of cycles by per amount of time. So I'm not going to demonstrate, why this is the case, but mathematically, what we can do, we can actually write that. So if I have a signal, f of t is my signal. What I've just told you means that I can write this as some sort of sum of cosine functions, where there's an amplitude term. So a of I would be the amplitude. And then there's going to be a frequency term. So we're going to write it as 2 pi f t. So f here is the frequency, t is the time. And then there's some phase. There's some phase, I'm going to call it phi I, the phase. So of course, it's an infinite sum. And so in reality, this is going to be written using an integral. So it's going to be written as this. It's going to be sum of a of f. So the amplitude of the cosine wave depends on the frequency. And then cosine of 2 pi ft plus phi of f. Okay. And actually, there's an even simpler way of writing this using complex numbers. And I will just write it here. But it's, it's not something you're supposed to know, but it's basically, you can write it as the amplitude of a of f e to the minus 2 pi ft. And just a small correction here, actually, this would be a plus sign here. Okay. So so we call the Fourier transform. We call this the Fourier transform. So A here, which I wrote as basically it's a combination of the amplitude and the phase of those cosine wave, is called the Fourier transform. And basically it's another way of representing a signal. So if I know if I know A, the signal A, there's another formula that allows me to completely and perfectly reconstruct the function f. So I can go from f of t, and I can obtain some a of f, which is the frequency information, using this Fourier transform. And then I can also apply an inverse Fourier transform and go from the information in the Fourier domain back into the temporal or spatial domain. So this is the inverse Fourier transform. So, so now what I can do is I can represent the spectrum of the signal. So we talk about spectrum. So spectrum is a plot that will show on the x-axis, we're going to show frequencies. So these are going to be our frequencies, f, with the 0 frequency in the center. And then on the y-axis, we're going to show the amplitude corresponding to that frequency. So this is going to be showing the amplitude. Okay. So if we assume, again, I'm going to go back here, and so if we assume a signal in the temporal domain, which is f of t, okay, which is a real signal, then we compute the different sine waves that the signal can be decomposed in. So we have all those, we have the low frequencies here, and then we may have the high frequencies. Each time for each frequency, we can measure the amplitude, and then we can plot that here. So for example, this will be a high frequency signal, and there may be a low frequency, and then all the frequencies in between, okay? And actually there's most signals that are real have an infinite number of different frequencies in them. Of course, you can have a signal that's a pure tone, for example, a musical tone that has a single frequency in it, and then it will have only information in that one frequency. But most signals in real world contain noise, and they contain essentially an infinite number of frequencies in them. And so if I'm going to draw my spectrum, I'm going to draw it like this, right? So this is essentially all the frequencies that are contained in that signal. And I want you to notice here that I made actually the spectrum symmetrical, right? So for a real world signal, so meaning actually a signal that is only composed of real valued numbers, the spectrum will always be symmetrical, okay? And so we only need to know the positive side of the spectrum, because the negative side is just the mirror image. And so here, this is my spectrum. And so we sometimes call the 0 frequency the DC term. So it's a name you may see, like the DC term is the 0 frequency. And the DC term corresponds to the average of the signal. So it's what's the sort of the overall offset. If you were to average the signal completely, what's the offset? And essentially it corresponds to a cosine wave that has 0 frequency. So it's a cosine wave with 0 frequency. If we write it down, simply would be cos of 2 pi times 0 times t, which is just 1. Okay, so what we call the DC term is just a constant offset that's applied to the signal, and it's the mean value of the signal. So now I would like to move on and try to apply this concept of frequency to images, right? So what about 2D images? So if we have a 2D image, like I said, is a array of values. two-dimensional function. But one way of looking at images is actually as a collection of one-dimensional signal. So I can take, for example, the rows of the image, and each row of the image is a one-dimensional signal, okay? So I could take a given image and then apply a Fourier transform on the rows of the images. And that will give us the frequency content of the image along the rows, which is the horizontal direction, right? So if we did that, we would end up with a collection of spectrums. So one spectrum for each row of the image, okay? So in that case, now we know if we look at the units, so on the x-axis, we have information in terms of frequency. So we're going to call it kx. That's going to be spatial frequencies. So kx is spatial frequency. And spatial frequency is in units of inverse space. Typically, we're going to talk about inverse centimeters because the image is going to be in centimeters. And in that case here, no, we still have, on the y-axis, we still have spatial coordinates, which are in units of centimeters. Okay. So alternatively, we could look at the image and also decompose it in terms of the rows, so not the rows, the columns of the image matrix. So we could look at the individual rows that make up the image matrix and again apply Fourier transform, but this time we apply it vertically. And then we're going to get the spectrum essentially are going to be along this direction. So now we have ky here. And now here we have x, okay? And what's interesting is we can also do is we can apply both. We can apply the Fourier transform on the rows of the image or the columns of the image. Sorry, on the rows of the image and then on the column of the image. So taking those spectrums and essentially turning it into, so we have rows here, we can turn it into columns, such as this here. So I'm going to turn these rows into columns by just chopping the image into a different orientation. And so now what we have here is, remember, so horizontally we have spatial frequencies. So you know, let's put another one here. So we could say, for example, this is our zero frequency, which we call the DC term. So this is all the DC terms in the image. And then we have, these would be sort of lower, so these ones would be lower frequencies and these ones would be higher frequencies. And we're going to apply the Fourier transform vertically now this time. So we're going to do F Fourier transform, applying the Fourier transform one by one on each column. We apply the Fourier transform one after the next. And so this is going to give us now a 2D structure where we have frequency information both on the x-axis and the y-axis. So we still have frequency information on the x-axis, but now because we took a Fourier transform along the y-axis, we are going to have frequency information on the y-axis as well. And so in this diagram now we have the low frequencies are going to be in the center. So this is our zero frequency is going to be right in the center. So this is the DC term is now a single element is the DC spot. And then we have different types of frequencies. So for example, the elements here represent frequencies that have a high rate of cycling horizontally, but no cycling vertically, because all along these lines, there's there's no spatial frequencies in the vertical direction, but there are spatial frequencies in the horizontal direction. And then if we look at this one here, this is going to be an example where we have no spatial frequencies in the horizontal direction, but spatial frequencies in the vertical direction. And then we can have a combination of the both. So we can have points here where we have a mixture of vertical and horizontal frequencies. Okay, so now let's look at what this looks like in practice. Okay, so this is a picture that's included in the lecture notes. And so this is actually showing examples of spatial frequencies and what they look like, both in the frequency domain and in the spatial domain. So this first example here, we have a alternating stripes that are aligned vertically. And so these stripes, this is actually corresponding to a cosine wave that's going in the vertical direction. And in frequency domain, there's essentially only information or only a non-zero component at this value here, okay? And because remember the spectrum is always symmetrical, there's the symmetrical copy of it that's on the opposite side of the spectrum, 180 degree away. So now the second one here that's shown in the second row has, again, alternating stripes, but this time the stripes alternates across the horizontal dimension. And also the stripes are more closely alternating. So the repetition rate is faster. That means there's higher frequency. And so when we look at the spectrum, the 2D spectrum that's obtained through this two-dimensional Fourier transform, you can see that the amplitude of the corresponding to non-zero, the point that have non-zero amplitudes are on the, first of all, you can see they are on the axis here. So these are the images that have no vertical frequencies. And this is because if you look at this image, there's no variation of the image along the vertical direction. But there's variation of the images along the horizontal direction, and especially this, the variation here occurs at these very specific frequencies that are shown on the diagram. And if we were to add up the two images, then essentially will be the same as adding the spectrum. And also this image shown here contains both vertical and horizontal frequencies. And it can be seen here that we have in the spectrum both those vertical and horizontal frequencies. And then here finally I show, so this is the DC term, the zero frequency, and basically it just corresponds to a completely flat image that has a constant value across all pixels. That's called that's the DC term. Okay, so now we're moving back here. So here, in those spectrums, I wanted to mention that I'm really showing only the amplitude information. But as you recall, there's always a phase information as well. And so I should also add up here that as a function of frequency, we can also plot phase. So phase would be here, and phase will be basically between -pi and pi. So phase in this case is an offset, and because we're talking about a cosine wave, anything that's greater than pi or smaller than -pi can be is equivalent to a value that's within the interval. And so the phase is kind of harder to really understand or to intuitively, but for any signal, it's going to have some kind of phase information associated with it that takes values between -pi and +pi. There you go. So now I'll show some examples of natural images and what we can understand from the spectra of these images. Okay, so now I'm going to show examples here of the frequency information content of real images. So this is a script in MATLAB, and I will make that script available on the course webpage. And we're looking at a picture of zebras, as you see here. And so this is the image I downloaded from the internet, and I put it into MATLAB. And MATLAB allows you to calculate the 2D Fourier transform, and looking at the Fourier transform across both the X and Y direction. And this is what I've done here. So this second picture here is showing you the Fourier transform of the zebra picture. And you can see these are the amplitudes of the image at different frequencies, both Kx, which is the horizontal frequency, and Ky, the vertical frequencies. I've also shown on the bottom picture here, this is the phase for that image. And as you can appreciate, it is in a way a little bit less intuitive to look at the phase information than than the amplitude information. So what I'm going to do here with this script is allows me actually to kind of isolate specific regions of the spectrum and to look what those regions of the spectrum encode in terms of the image. So I'm going to just circle out, to start with, I'm going to circle out this very center of the spectrum here, the signal that's right at the center of the spectrum. And so you can see in the second column here that these frequencies that are in the center of the spectrum essentially encode coarse details of the image, right? So these are, they can tell the image is very blurry. There's very little detail in that image. And so all that information that's encoded in the center of the spectra are the low frequency details, the coarse details. And then in that third column, what I'm plotting is actually this residual. So what is the rest of the spectra encoding? And you can see that the rest of the spectra is encoding mainly the finer details. And so you can appreciate here the image of the zebra really highlighting the fine details that are left. Okay. So I'm going to look at a different portion of the spectra now. Again, remember that the spectra is symmetrical. So this part of the spectra is mirrored on this side of the spectra. And I'm going to look this time specifically at this region of the spectra here. There's a region that has higher amplitude. And so you can see that this region of the spectra really seems to be encoding those stripes. So of course I choose the picture with a lot of stripes so that it would have some interesting features in the spectrum. And you can really see by selecting this region of the spectra, now we're really seeing this type of information that's being encoded by the spectrum. Let's see, I'm going to look at a last one. So this time what I could do is I could actually select a region of the spectra that doesn't have anything, shown here. So here, this is a region of spectra that's pretty empty. There's not much energy in this region of the spectrum. And you can see that doesn't really contain anything of importance. It probably mainly is noise. And actually, so the residual, the image that does not contain this part of the spectra is almost identical to the original image. Okay, so this region of the spectra could essentially be ignored because it doesn't really contain much information that's of use for understanding this image. So now I'd like to just recap basically this short video. So what we talked about that's important to remember is that if we have any signal that's real, shown here, it can be decomposed into some of different pure frequency signals, which are sine waves. Each sine wave has a phase, an amplitude, and a frequency. And so we can write that as an infinite sum using an integral here. And we can go back and forth between the signal in the temporal domain shown here and the signal in the frequency domain shown here. And so when we go from the temporal domain to the frequency domain, it's called a Fourier transform. And then when we take the frequency spectrum back into the spatial domain, it's called an inverse Fourier transform. And so what we have as when you do a Fourier transform, we get the amplitude of the signal as a function of frequency. And there's also a phase also as a function of frequency. And we can go back and forth between the two. So then when we talk about images, the same thing applies. We can take an image and we can apply two consecutive Fourier transform, first on the rows of the image and then on the column of the image, or vice versa. It actually doesn't matter if we do the rows first or the columns first. And we obtain something called a two-dimensional Fourier transform, which is a spectrum that is a function of spatial frequencies in the x direction and the y direction. And there's actually something called a 2D Fourier transform, which I didn't mention, but you can jump directly from the image all the way to the Fourier transform in a single step. And so this frequency information that's available through the Fourier transform is another way of looking at images. And when we reconstruct images, we'll see that we can actually derive mathematically a formula to reconstruct three-dimensional images from the measurement are given by the scanner. So this is why this is going to be interesting. Okay, so this is the end of the lecture. Hope you enjoyed it. I will be discussing this a little bit more in class, but I think it's useful that you've seen that before class. So thank you for watching.